knows a lot about the science stuff. Professor Dave explains.
The Henry reaction was first reported by Belgian chemist Louis Henry in 1895. It involves the addition of a nitronate salt to a carbonyl compound, usually an aldehyde. The reaction is also sometimes referred to as a nitroaldol reaction. In the previous tutorial on the Neff reaction, we saw that aliphatic nitro compounds are carbon acids. In water, they have a pKa of around 10, meaning they are as acidic as some 1,3-dicarbonyls, like malanates, and can therefore engage in carbanion chemistry. The nitronate is usually prepared in situ by treating the nitroalkane with a strong base, like hydroxide, alkoxide, or even a strong amine base. Typically, a catalytic amount of base is sufficient because the alkoxide first produced should be basic enough to deprotonate more nitroalkane and perpetuate the reaction. Thus, the reaction illustrated here can be run in one pot. We must also keep in mind that the reaction is readily reversible, with this product going back to the nitronate and aldehyde, and nitroaldol reactions that seem slow are often simply hindered by unfavorable equilibria. For example, Henry reactions with ketones can be unsatisfactory or even impossible due to the fact that the equilibrium lies in favor of the nitronate and the ketone. The use of aldehydes as reactants also brings the danger of base-promoted reactions like aldol condensations and Cannizzaro reactions of the aldehyde. We have discussed these reactions in previous tutorials, so refer to those if you need to review your knowledge of aldehyde chemistry under basic conditions. As we are aware of these possibilities, a reaction like this must be carefully optimized. In rare cases, the Henry reaction is even too favorable and can occur twice because the product is itself a nitroalkane. This overreaction is encountered almost exclusively with formaldehyde, and in these cases, a 2-nitro-1,3-diol is formed, which can sometimes have synthetic value. 1,2-nitroalcohols are important intermediates in organic synthesis. We already know the Neff reaction. With this technique, 1,2-nitroalcohols can be converted to alpha-hydroxyketones as shown in path A, a type of transformation which we can refer to with the German term Umpolung, or inversion of polarity, because it is equivalent to the addition of an acyl anion to an aldehyde, an operation which cannot be carried out directly. In addition to this, the nitro group is easily reduced to the amine, and therefore this is a route to 1,2-amino alcohols, as is shown in path B. The Henry product can also be easily dehydrated to a nitroolefin, as in path C, which is a Michael acceptor and can be reacted at this position with a number of nucleophiles. So this reaction, especially due to the utility of the nitro functional group, is a very versatile tool and is used extensively by organic chemists. An example of a tandem Henry plus Neff reaction is the one-carbon homologation of pentoses to hexoses, meaning that a carbon is being added to go from a 5-carbon sugar to a 6-carbon sugar. As we know from the biochemistry series, cyclic sugars are in equilibrium with an open chain form, which features an aldehyde group, and as such they are substrates for Henry reactions, like that with nitromethane. In situ Neff reaction leads to a one-carbon homologation, since the carbon originally from nitromethane will attack this carbonyl to get the new hydroxyl. And then when water attacks, as in the Neff reaction, nitrogen is kicked off and we get the new carbonyl. In this particular example, we can see that D-arabinose is homologated to yield a mixture of D-glucose and D-mannose. Such a mixture arises because the stereochemistry of the addition of the nitronate to the arabinose aldehyde form is not controlled, and therefore gives rise to a mixture of diastereoisomers. Let's look at another interesting application. An example of the double Henry reaction was reported by Lei Yao at the School of Pharmacy of Yantai University in China. This reaction allows for the efficient synthesis of an important therapeutic agent against multiple sclerosis, fingolimod. we can see that 2 equivalents of formaldehyde will be necessary, and we end up with the 2 hydroxyl groups, followed by reduction of the nitro group. Now, as we may have realized by this point, it is the case that the Henry reaction can create up to 2 new stereocenters. Stereoselective synthesis has been a major challenge for organic chemists over the last 50 years or so, which more recently has delivered excellent results. So it is not surprising that the Henry reaction has been a prime target for diastereoselective and enantioselective synthesis. To illustrate some of the efforts in this area, we will highlight the breakthrough work of Professor Masakatsu Shibasaki, who now works at the MCRF Institute in Tokyo. Beginning in the 1990s, he found that bienol metal catalysts, best if derivatives of lanthanides, create a chelated, rigid transition state for the reaction, and therefore allow for excellent stereo control. For example, in his synthesis of 3-dehydrosphingosine, he obtained the desired product in about 90% selectivity. The syn product dominates over the 2 anti-nitroaldols in a ratio of 91:9, and within the 2 syn products, enantioselectivity is almost complete. Later, the nitro group is reduced to an amine, illustrating the application of the Henry reaction to amino alcohols of biological significance. Shibasaki used lanthanum trichloride as the central metal to organize 3 bienol ligands around the core center. Later, other metals have been used with a similar design. In addition, completely different catalytic approaches have been used by other researchers, who have extended the work to chiral aldehydes. This field is far too vast for us to continue to discuss here, as the old Henry reaction is still a hot topic of research in modern organic synthesis, as well as a frequent topic of discussion in organic chemistry courses and exams. It certainly belongs to the list of the name reactions every organic chemist should be familiar with.
Thanks for watching. Subscribe to my channel for more tutorials. Support me on Patreon so I can keep making content. And as always, feel free to email me, ProfessorDaveExplains@gmail.com.